Hi, and welcome to this video on specific heat capacity and specific latent heat. Although both of these terms are a bit of a mouthful to say, by the end of this video, you'll see that the ideas they represent are pretty straightforward and even kind of useful. In our video on solids, liquids and gases, we saw that the internal energy of a system is the total amount of kinetic and potential energy of the particles it contains. Transferring heat energy to a system increases its internal energy, which can have one of two effects: to increase the temperature of the system or to cause a change of state. The topic of specific heat capacity is to do with the first of these effects, and specific latent heat is to do with the second, so the rest of this video will be split into these two main sections. Let's say you are transferring some heat energy to a substance. What factors affect by how much the temperature of the substance will increase? Obviously, the more heat energy you supply, the hotter the substance should get, and the mass of the substance is going to be important too. The more particles it contains, the more energy we're going to have to supply to get them up to a particular temperature. Finally, the type of material will also affect how hot it gets. Mathematically, this factor is represented by a quantity called the specific heat capacity of the material. The specific heat capacity of a material is the amount of energy it takes to increase the temperature of 1 kilogram of that material by 1 degree Celsius. We might say, for example, that the specific heat capacity of aluminium is 900 joules per kilogram per degree Celsius. What this means is that it takes 900 joules of energy to increase the temperature of 1 kilogram of aluminium by 1 degree Celsius. Iron, on the other hand, has a lower specific heat capacity of 450 joules per kilogram per degree Celsius, which means that supplying 900 joules of energy to 1 kilogram of iron will cause its temperature to rise by 2 degrees. Liquid water has a remarkably high specific heat capacity of 4,200 joules per kilogram per degree Celsius, which helps explain why boiling a full kettle at home to make just a single cup of tea is really bad for your electricity bill. The equation for specific heat capacity looks like this. We should remember here that the Greek letter delta stands for the change in something. So delta E is the change in thermal energy, which is measured in joules. M is the mass in kilograms. C is the specific heat capacity, which, as we saw, is measured in joules per kilogram per degree Celsius. And finally, delta theta is the change in temperature in degrees Celsius. Let's go through a quick example which uses this equation. As you can see, we're given the mass of the water, its specific heat capacity, and its increase in temperature, so this should be a straightforward substitution question. Before subbing in though, we should convert the mass to kilograms and work out the value of delta theta, which is just 85 degrees Celsius. From there, using our equation and subbing in, that becomes 0.3 times 4200 times 85 to give a final answer of 107,100 joules, or in kilojoules, 107.1 kilojoules. This question is a little different because here heat energy is being lost from the saucepan. As you can see, it starts out at a temperature of 120 degrees Celsius, and we need to work out its final temperature, which is going to be lower than this, so let's get started. Our equation again is delta E equals mc delta theta. Here, because the saucepan is losing energy, delta E will be negative, so on the left hand side we can write minus 108,000 joules, and on the right equals 1.2 times 900 times delta theta. Just working through, our next line looks like this, and then solving for delta theta, the change in temperature becomes minus 108,000 divided by 1080 to give minus 100 degrees Celsius. In other words, the temperature of the saucepan dropped by 100 degrees Celsius, which means that its final temperature is 120 minus 100 to give a final answer of 20 degrees Celsius. From these two examples, we can see the useful kinds of calculations which we can do when we know the specific heat capacity of a material. But how do we actually measure specific heat capacity? Have a look at this equipment, which is being used to measure the specific heat capacity of the material this cylinder is made from. We know that the equation for specific heat capacity is C equals delta E divided by m delta theta. So to calculate the specific heat capacity of the material, we need to measure the amount of heat energy supplied to it, its mass, and its change in temperature. You can see that the heater which has been placed into the cylinder is connected to the main supply via a joule meter. As the name suggests, this device allows us to measure the amount of electrical energy which has been supplied to the heater. Here, we can assume that the heater is 100% efficient and that all of the heat energy it releases is transferred to the metal cylinder. So now, we have the value of delta E. The values of m and delta theta are easier to measure. We just use a balance to measure the mass of the cylinder, while its temperature increase is as shown on the thermometer. Once we have all three values, we just plug them into the equation to find the specific heat capacity of the material. Let's have a look through this example now to see how this works. Our equation again is delta E equals mc delta theta, which we rearrange to give C equals delta E divided by m delta theta. Here, we can see that the amount of energy transferred to the steel was 7,840 joules, its mass was 0.4 kilograms, and its increase in temperature was 40 degrees Celsius, so that gives a value for its specific heat capacity of 490 joules per kilogram per degree Celsius. So far, we've looked at how changing the internal energy of a system can cause its temperature to change, but as we mentioned at the start of this video, under the right conditions, changing the internal energy of a system can also cause a change of state, and that's where the idea of latent heat comes in. Let's say we're heating up some water from room temperature. It doesn't matter whether we're using a kettle or a Bunsen burner or some other method to do so. As we supply heat energy to the water, its temperature rises. When it reaches its boiling point, however, which is at 100 degrees Celsius at standard atmospheric pressure, something surprising happens. The temperature of the water stops rising. Here, although we're supplying more and more heat energy to the liquid water, its temperature is refusing to rise beyond 100 degrees Celsius. It's only once the water has changed from a liquid to a gas that its temperature starts to rise again. But why? To explain where this energy is going to, we have to go back to our old friend, the particle diagram. Remember that, in a liquid, the particles are still packed quite closely, and the bonds between them are fairly strong. To allow these particles to escape the surface of the liquid and form a gas, these bonds have to be broken, and that takes energy. So all the energy we've been putting into our water at 100 degrees Celsius while it was boiling is used to break the bonds between the particles in the liquid. The energy which is used to change the state of a substance is referred to as latent heat. The specific latent heat of a substance is the amount of energy needed to change 1 kilogram of the substance from one state to another with no change in temperature. The equation for specific latent heat looks like this. Here, E is the energy for a change of state, which is measured in joules. M is the mass of the substance in kilograms, and L is the specific latent heat in joules per kilogram. There are two types of specific latent heats which you need to know about for your exam. The specific latent heat of fusion, LF, is the amount of energy needed to change 1 kilogram of a substance from a solid into a liquid at the same temperature. The specific latent heat of vaporization, LV, is the amount of energy needed to change 1 kilogram of a substance from a liquid to a gas at the same temperature. As you can see, both definitions are pretty similar, so try not to get them mixed up. When you see vaporization, think vapor or gas. A setup like this can be used to measure the specific latent heat of vaporization of water. We first turn on the heater. As soon as the water reaches its boiling point, we reset the joule meter reading to 0 and record the mass of the beaker and the water inside. We then allow the water to continue to boil for a few minutes before recording the final balance and joule meter readings. The change in the mass reading gives us the value of m in our equation, which is the mass of water which changed state from liquid to gas, and the joule meter reading gives us the value of E. So a simple calculation will give us the value of LV, the specific latent heat of vaporization of water. Have a read through this example. As you can see, the initial mass of the beaker and water was 350 grams, but by the time 100 kilojoules of heat energy was transferred to the water, this value fell to 310 grams. That means that the mass of water which changed from a liquid to a gas was 40 grams or 0.04 kilograms. The equation again here is E equals mL, where it's the specific latent heat of vaporization that we're looking for. Rearranging, we have LV equals E divided by M, and subbing in, that becomes 100,000 joules divided by 0.04 kilograms to give a final answer of 2,500,000 joules per kilogram, or in standard form 2.5 times 10 to the power of 6 joules per kilogram. It takes a huge amount of energy, 2.5 megajoules, to change 1 kilogram of water from a liquid to a gas. Remember that it takes just 4.2 kilojoules to increase the temperature of liquid water by 1 degree Celsius at standard atmospheric pressure. One last example for this video, so why don't you pause here, give it a go, and then press play when you're done. We can see that the melting point of stearic acid is at 69 degrees Celsius. What that means is that in the top section of the graph, this substance is a liquid, and in the bottom, it's a solid. And so that means that the middle flat section of the graph tells us where it's changing state from liquid to a solid, or in other words, where it's freezing. From our graph, we can see that while the stearic acid was freezing, it transferred 20 kilojoules of energy to its surroundings. This is the energy value which we use in E equals m times LF. So rearranging to find the mass, we have m equals E divided by LF, then subbing in, that becomes 20,000 joules divided by 2 times 10 to the power of 5 joules per kilogram to give a mass of 0.1 kilograms. So far, we've only talked about changes of state which involve increases in internal energy, so solid to liquid and liquid to gas. In both cases, energy or latent heat must be supplied to the substance to allow the change of state to occur. This explains why sweating helps keep us cool. As liquid water evaporates from the surface of our skin, it carries away with it heat energy in the form of the specific latent heat of vaporization. For changes of state which involve a decrease in the internal energy of the system, such as condensation and freezing, latent heat energy is released as new bonds are formed. This explains why being burnt by steam, which is at 100 degrees Celsius, is much more painful than being burnt by liquid water, which is at the same temperature. I'll bet you never thought you would have heard the word specific used so many times in one video. Aren't you lucky? Seriously though, although lots of students find this topic difficult, you really can't go wrong as long as you learn and understand the definitions, know how to use the equations, and work through the practice exam questions. Good luck!